All right. Hello, everyone. Um, I'm going to try to record a video in a little bit of a new fashion, some new software. So let's see how it goes. This is Mr. Melillo, and we are in Unit 1.5 of Algebra 2, and this is a mini lesson on beginning how to deal with perfect squares and the idea of completing the square. So up until this point in our unit 1.5 or our quadratics unit, we have um, learned to use factored form. We have learned to use standard form. And we can go back and forth between the two, whether we're factoring or whether we're distributing. Our next set of lessons involves dealing now with vertex form. And so vertex form, if you recall, let's see if I can get my drawing to work, is, if you recall, a x minus h squared plus k, y equals. And so what we want to be able to do is to write an equation in this form when you're given one in either standard form or vertex form. Why would we want to do that? Well, uh, the idea is we can write it by and quickly to find the vertex. This function has several advantages by using the vertex, so it is a good skill to be able to do. And also, one of the more powerful reasons as well that we're going to work with is when an equation is in vertex form, it actually becomes easier to find x-intercepts that are not whole numbers. So, for instance, like if you had an equation like this, like x plus 3 times x minus 4, we know that that has intercepts of -3 and +4. But as we said before, not every equation has a factored form that's nice like this. When it doesn't, this is not very good at finding x-intercepts, but vertex form is. So that's the ultimate end goal for this. But we're going to start with a quick lesson um, involving perfect squares, okay? And not just involving numbers, like we know some of the perfect square numbers perhaps, but also just algebraic perfect squares. Okay, can I go to the next slide? Oh, here we go. Okay, all right, so a bit of a warm up here. What are we squaring? Do excuse me if I cough a bit. So in each equation, which expression could be substituted for a so that the equation is true for all values of x? Okay, so you do want to, the whole idea here is we're going to learn to recognize squares from things that are not necessarily numbers, but they're also algebraic constructs. So, like, for example, like we're trying to substitute something in for a, right? So, what would you replace the a with so that this is a true statement? Well, in order for this to be a true statement, you'd have to have the same thing equals the same thing. So, like, for example, if I took this a and replaced it with an x, then the equation would be true for both sides. So I would say that in this particular case, I would say that a equals x. So if I took the a and replaced it with an x, then I'd have x squared equals x squared, which is clearly a true statement. Okay, so looking at a few other ones here now, um, if you have 3x and it's been squared, what's the thing that's actually been squared? Well, clearly it's 3x. So in this case, a equals 3x. And you kind of see where we're going. We're learning to see like what is being substituted into what expression. What about this one? Let's see. Something is being squared here. What here is being squared? Well, okay, no exponent, right? Well, let's think about this. The definition of squaring is multiplying it by itself. So, what if we rewrote this as 7x squared? Then it's clear here that a is equal to 7x. Okay. All right, let's keep going here. So what about this one? 25x squared equals a squared. Oh, well, that's just the same as the last one, right? Because, 7x. Ah, but wait. Notice with this one, there's a lack of parentheses here. So the 25 is separate from the x squared. So is 25 by itself a perfect square? Well, why, yes, it is. So it turns out that 25 is 5 squared. And then x squared equals a squared. And at this point, knowing this, it might become a little bit clear here that a is equal to 5x. Because if I took 5x and squared it, and I were to take 5x multiplied by 5x, I would get 25x squared without the parentheses. So this starts to get a little bit more into how we're going to be approaching this. We have to figure out how an expression like this can be written as the square of a single term. Okay, same idea. What about this one? What multiplied by itself gives you 1/4 x squared? Well, let's see. 1/4. 1/4 is square? Well, 4 is a square. 4 is the square of 2. So this must be, 1/2 squared is equal to 1/4, right? So 1/2 x squared must be 1/4 x squared. So again, if I have a term of 1/4 x squared, the 1/4 has a square root. It's 1/2. Okay. Now, what if we get to expressions like this? If I have something that's squared and the thing that's squared over here is x plus 1, well, that's just a straight up replacement, right? So I know that a equals x plus 1. What about down here? Remember, the definition from before, something squared is multiplied by itself. So that must mean that we have 2x minus 9 squared. And so a equals 2x minus 9. See? Okay, so recognizing from each expression, the idea is, can you recognize what thing has been squared? Okay, let's keep going. All right, each expression is written as the product of factors. Write an equivalent expression in standard form. Okay, so standard form, right? Standard form essentially means that you've broken things apart and there's no parentheses. So like, for example, if I have 3x in parentheses and that's been squared, what is 3x times 3x? Well, that would be 9x squared. See how the 3 gets multiplied by itself as well, as does the x. Okay, let's keep going. 7x times 7x? Well, we can just multiply that together, right? We get a 49x squared. Okay, x plus 4 times x plus 4. Ooh, let's do some distribution, right? X, so I get an x squared. Looks like we have a 4x, another 4x, and then a 16, all of which are added. And so what you end up with is x squared plus 8x plus 16. Okay, right? So again, nothing different than what we've already done. All right, what about this? Okay. So one common thing that a lot of people might do is they see x and then they see the 1. Oh, let's square them, right? So if you look at part A, we just squared the 3, we squared the x, and we got 9x squared. So here, let's do the same thing, and we get x squared plus 1 squared, or x plus 1. Ooh, guess what? That's wrong. Can't do that. Okay. And here's the reason. It turns out that exponents like this, they do not distribute across addition. Okay, so let me write that up here. Exponents do not distribute over addition or subtraction. Subtraction is, well, the reverse of addition, so that should be just trivial from that. Instead, because again, what does it mean to square something? The only way to handle this is to multiply it by itself. And so if we do x plus 1 times x plus 1, now we can multiply it. If you didn't do this, you would be missing the middle terms. So now let's multiply it out. We get an x squared. We get a 1x. We get another 1x. And we get 1 times 1 is 1. So we get x squared plus 2x plus 1. Okay. Now, just like before, we had two middle terms. And because we're using the same number twice, we got two of the same middle term. So it's like there's a double middle term. Okay. Let's try the next one. What if I did x minus 7 squared? X minus 7 times x minus 7, right? Again, don't just square the two terms. Multiply it out. We get x squared minus 7x minus another 7x plus 49. 7 times 7, negative 7 times negative 7 is a positive 49. And we get x squared minus 14x plus 49. And just like before, we get a double middle term. So this middle term seems to be double the numbers that we had before. So would it happen if we had n? When we notice a pattern like this and we think, hey, I've noticed that this result is consistent for a few different problems. Let's try it with n, because if the same pattern holds with a variable, then it's actually true for all numbers. So let's try it out. What if I did x plus n times x plus n? What would happen? Well, I would get x squared plus nx plus nx plus n squared. Now, nx plus nx, okay, like terms. If I have one apple and I add another apple, I have two apples. Hey, I get a double middle term. And because this n, the 2n is, well, double the term over here, this must mean that it works for all numbers. Fascinating. Okay. Why do you think the following expressions could be described as perfect squares? Now, here's the thing. 6 is not a perfect square number, but it turns out this is a perfect square. But why? Think of our factoring rules. What two numbers add to give you 6 and multiply to give you 9? It's 3 and 3, right? It's x plus 3 times x plus 3. So when I write this, I can get rid of one of the factors like this, and I can write it as, oops, I also seem to have changed color there, as x plus 3 squared. So this expression is the square of x plus 3, despite the fact that there's a 6 there, which we know is not a perfect square. How about this one? Now again, look at the pattern that we saw up here. And this is where it becomes pretty important here. Now, again, we know that we need to find two numbers that multiply to give you 64, right? So what are the most common choices? 8 and 8. And they have to add to a negative 16. So maybe minus 8 and minus 8. But if you have two of the same number, x minus 8 squared. So here's the trick. If you take this negative 16 and you cut it in half, you get a negative 8. And this negative 8, you square it, you get a 64. Then you know that's a perfect square. Same thing over here. If we look at this one, let's look at this one here, 36, right? So 1 over 36, well, what multiplied by itself gives you 36? 6, right? So what if we wrote this as x plus 1 over 6 squared? Now, does that work? 6 times 6 is 36. 1/6 times 1/6 is 1/36. That works. But is 1/6 plus 1/6 equal to 1/3? Well, that's 2/6, and that does in fact equal 1/3. So it does work. That all three of those are perfect squares. Even though 1/3 is nowhere near as perfect square as we would like, but it's part of an algebraic perfect square. Okay. So here's the kind of the summary of the whole thing, right? So it doesn't matter whether the expression contains numbers, variables, fractions. Remember, fractions are friends, not food. Uh, any terms that look along this lines, x plus 3 squared, x minus 8 squared, x plus 1/6 squared from above, like those three from above, whenever x plus n is squared and expanded, you get this. And here's the square to prove it. Now, likewise, the reverse is true. If you have an expression that appears to be written in this form, where you have a term that is a perfect square on the end, and the middle term is twice whatever that square root is, then we could write it as a perfect square. That's ultimately what we're going to come down to. So we're looking at it in this lesson, we're looking at it front ways. What does a perfect square mean for an expression? And then we're going to eventually look at it going the other way. Okay. All right. So here is some expressions, right? So Han and Jada solve the same equation with different methods. Okay. All right. So Han's method here. So let's look at what Han does. He takes x minus 6 squared equals 25. He writes it as two factors, x minus 6 equals 25. He multiplies it out. He then subtracts 25 from both sides. Why does he do that? So he gets the 0. Remember, with the 0, now we can use the 0 product property. Okay? And so when he does that, he gets an expression that factors, but in a different way. X minus 11, x minus 1, that adds to negative 12, multiplies to 11. And so his answers are 11 and 1. Okay. So this uses methods that we've done before. But now look at Jada's method. Look at this one. So x minus 6 squared equals 25. So in this particular one, he realizes that something squared has to equal 25. Well, what could that be? 5 squared equals 25, that's for sure. But negative 5 squared also equals 25. And so because of that, here we go. We have these two expressions right here. X plus 6 could equal 5, because 5 squared is 25. Or x minus 6 squared equals negative 5. And negative 5 squared equals 25. Adding 6 to both sides, 5 plus 6 is 11. Adding 6 to both sides, x equals 1. Well, now that's convenient. They get the same answer, but Jada's method's a lot less work. Ha. Okay. So, for this example, we can solve one using Han's method, one using Jada's method. Okay? Let's just do one of these, right? We don't need to make the video too long, so let's pick one, right? Let's do the first one, right? Okay, so let's have y minus 5 squared equals 49. Okay, so if we were to solve this with Jada's method, right? Actually, no, we could use Han's method first, right? So we can do this, we can write this out, and we get y minus 5. Oopsie. Let me erase that a little bit. Okay, let's fix that back. Okay, so y minus 5 times y minus 5 equals 49. Okay. So we're going to distribute here. Y squared minus 10y plus 25 equals 49. Okay. So in this particular case here, we get our factoring. We distribute it out. Let's subtract the 49 from both sides. We get the 0 on the end here, right? So 49 minus 25 is 24. So we're going to get y squared minus 10y minus 24 equals 0, because I subtracted the 49 from both sides. Now this is going to factor. Let's come over here. What two numbers add to negative 10? Multiply to negative 24. Ooh, 12 and 2. So let's do that. We're going to have y minus 12 and y plus 2 equals 0. And so we get y equals 12 and y equals negative 2. Okay. Now, all right, so that was a fair amount of work. Now again, let's try that with Jada's method. And so I'm going to go ahead and erase. Let's erase most of the work here. Okay, this is not as free. Okay, not as free form as I would like, but that's okay. Takes a minute to erase everything with this one. But hey, you know, the fact that I can write it out is on here and make a video is pretty cool. So I'm willing to let it slide. Okay, now let's solve that one using Jada's method, right? And so now what we're going to do is we're going to take the square root of both sides. Now, what times what gives you 49? Could be 7, could be negative 7. So I'm going to say y minus 5 equals 7, and y minus 5 equals negative 7. Okay, and for both equations, I'm going to add 5 to both sides. And so I get 7 plus 5, I get y equals 12. And I add 5 to both sides, and I get y equals negative 2. Just like that. So, turns out vertex form, because you might recognize that as vertex form, turns out this kind of form it can get you x-intercepts sometimes faster than even factored form can. Interesting. Okay, last one, because this fraction one, let's do the fraction one while we're on here, just so that you get some experience at doing that. And then we'll move on. Okay. Okay, so let's get rid of this. Hey, and there's actually another fun thing with Jada's method. There is less to erase. Imagine that. Okay, perfect. Okay, so let's go ahead and do this with Jada's method now that we see that it's definitely appears to be easier, right? Okay, so let's do drawing. Let's do this time. Okay, so z plus 1/3 squared equals 4/9. Well, what squared gets you 4/9? Well, let's see. 2 times 2 is 4, and 3 times 3 is 9. So 2/3 squared will be 4/9. So z plus 1/3 is going to equal 2/3, or z plus 1/3 equals negative 2/3. Because 2/3 multiplied by itself is what's giving us the 4/9. And it could either be positive or it could either be negative. So now in this particular case, I can subtract 1/3 from both sides. What is 2/3 minus 1/3? 1/3, so z is 1/3. Or what if I have negative 2/3 and I subtract 1/3? I have negative 3/3, which is negative 1. And both answers are correct. So this appears to be a lot faster. Excellent. Okay. So here's a quick summary for you, right? Okay, so a perfect square is an expression that is something multiplied by itself. Usually, we are interested in situations here where that something that's being squared is like a rational number or an expression with rational coefficients. And so the quick summary here, these expressions are perfect squares, even though the middle number doesn't appear to be a perfect square. X plus n squared is equivalent to x squared plus 2nx plus n squared. That middle term is double what the number inside the parentheses was. Okay. All right. And so finally, quadratic equations that are in the form of a perfect square equaling a perfect square can be solved in a supremely straightforward manner. And so this is why we did the warm-up early, where we had the squares on both sides. So here you have an expression x squared minus 18x plus 81 equals 25. If we can write it as a perfect square, all we simply have to do is realize that 5 times 5 gives you 25, and it breaks down into two immediate equations. X minus 9 equals 5, x minus 9 equals negative 5. And from that, we get our two solutions. So this is going to form the basis of the rest of this little kind of mini unit as we learn how to complete the square and solve a different group of quadratic equations that involve the vertex. All right. Hope this has been informative, and I will see you guys in class. Have fun.